Hello everyone and welcome to Sally and Bytes. Today, I am here to teach Relational Database and SQL, Part 5, SQL Data Types, difference between CHAR and VARCHAR data types, and constraints in SQL for the Class 12 students of Computer Science. So, let's dive in and get started. SQL, Structured Query Language, supports various data types to store and manipulate different types of data in a relational database. In SQL, each column of the table is assigned a data type which conveys the kind of value that will be stored in the column. Within MySQL, data types are organized into several categories, including numeric, non-numeric, often referred to as string types, date, and time types. While MySQL offers a wide range of data types under each of these categories, we will concentrate on some commonly used data types in MySQL. The numeric data type integer. The integer data type is capable of storing and representing whole numbers, which can be either positive or negative. It accommodates positive whole numbers with up to 11 digits and negative whole numbers with up to 10 digits. The allowable range of integers spans from -2,147,483,648, approximately -2 billion, to 2,147,483,647, approximately 2 billion. The syntax is uppercase integer or lowercase integer. The next data type is float data type. Float data type holds numbers with decimal points. Each float value occupies 4 bytes, 32 bits in memory of storage space. This data type is suitable for representing values with both whole and fractional parts, making it versatile for various numerical applications. The syntax is uppercase float or lowercase float. Data type numeric. This is quite interesting. Numeric of P(s) data type is used to represent fixed point numbers with a specified precision and scale. Here's what P and S represent. P represents the total number of digits, both to the left and right of the decimal point, that can be stored in the number. It is often referred to as the precision. It indicates the maximum number of digits in the number, including both the integer part and the decimal part. S represents the number of digits to the right of the decimal point. It is often referred to as the scale. It indicates the maximum number of decimal places that can be stored in the number. The syntax is numeric of P(s). It takes 2 arguments: precision of P and scale of S. Let's see some examples. Numeric of 6,2. This specifies a numeric data type with a total precision, P, of 6 digits, and the scale, S, is 2, indicating exactly 2 digits to the right of the decimal point. Remember that numeric determines the exact precision and scale. Let's see the value 1234.67. Here the total number of digits, both to the left and right of the decimal point, is 6, that is, precision is 6. The number of digits to the right of the decimal point called scale, which is 2. This fits perfectly within the numeric of 6,2 data type, as it matches the specified precision of 6 with 2 digits to the right of the decimal point. Now, let's see the next value. 123.45. Here, the total number of digits, both to the left and right of the decimal point, is 5, that is, precision is 5. The number of digits to the right of the decimal point called scale, which is 2. This fits perfectly within the numeric of 6,2 data type, as it within the specified precision of 6 with 2 digits to the right of the decimal point. Let's see value 123.456. Here, the total number of digits, both to the left and right of the decimal point, is 6, that is, precision is 6. The number of digits to the right of the decimal point called scale, which is 3. This results in an error as it does not fit perfectly within the numeric of 6,2 data type, as the decimal part should be 2 digits on the right of the decimal point. But here it is 3 digits on the right of the decimal point. The next data type is decimal. Decimal of p, s data type is used to represent fixed point numbers with a specified precision and scale. Here's what p and s represent. P represents the total number of digits, both to the left and right of the decimal point, that can be stored in the number. It is often referred to as the precision. It indicates the maximum number of digits in the number, including both the integer part and the decimal part. The precision can be equal to or greater than what is specified by the coder, and the actual precision may vary depending on the database system. S represents the number of digits to the right of the decimal point. It is often referred to as the scale. It indicates the maximum number of decimal places that can be stored in the number. The syntax is decimal of p, s, or decimal of size, precision, or decimal point. Let's see some examples. Decimal of 6,2 specifies a decimal data type with a scale of 2, exactly 2 digits to the right of the decimal point. However, the precision can be equal to or greater than 6, and the actual precision may vary depending on the database system. Remember that decimal specifies only the exact scale. The precision is equal or greater than what is specified by the coder. Example. Look at value 1. A value like 1234.56 will be stored as is, with 4 digits in the integer part and 2 in the decimal part. So total of 6 digits, 2 to the right of the decimal point. This fits perfectly within the decimal of 6,2 data type. Now look at value 2. A value like 123456.78 will also be stored with 6 digits in the integer part and 2 in the decimal part, even though the precision is greater than 6. Here, the total number of digits, that is the precision, is 8 digits. It accepts the precision given as 8 digits. The precision can be equal to or greater than what is specified by the coder, and the actual precision may vary depending on the database system. Now, look at value 3. A value like 1234.567. This results in an error as it does not fit perfectly within the decimal of 6,2 data type, as the decimal part should be 2 digits on the right of the decimal point. But here it is 3 digits on the right of the decimal point. So, can you find the difference between numeric of p, s and decimal of p, s? Yes. There is a small difference between them. Numeric determines the exact precision and scale. Whereas decimal specifies only the exact scale, the precision is equal or greater than what is specified by the coder. Decimal columns can have a larger than specified precision if this is more convenient or efficient for the database system. Next data type is character of fixed length. CHAR data type stores X number of characters in the string which has a fixed length. A maximum of 254 characters can be stored in a string. If you store strings that are not as long as the size or X parameter value, the remaining spaces are left unused. The syntax is char of X or char of size. Let's see an example. If you specify name char of 10, name equals Sam, the string Sam is 3 characters. So 3 plus 7 unused spaces are stored as 10 characters in total. So it takes 10 bytes of storage. Char data type takes memory space of 1 byte per character. As the value of string Sam is 3, the remaining 7 spaces are left unused and blanks are added. So when we want to add a name, we cannot assume the number of characters. Example, John can have 4 characters and Sophia can have 6 characters. So char data type can be used for fixed length of string. Now look at example 2. However, a student admission underscore number is 6 digits long in a school. So char of 6 would be appropriate to store the admission underscore number of all the students. Another example is PIN code of a country. So char data type is suitable where the number of characters to store is fixed. The value for char data type has to be enclosed in single or double quotation marks. The next data type is character of variable length. VARCHAR data type is used to store variable length alphanumeric data. Advantage is VARCHAR data type will not leave unused spaces like the char data type. It releases the unused memory spaces. The syntax is VARCHAR of x, example. Name VARCHAR of 10. Name equals Sam, you can look at the picture. It has taken only the length of the string 3 bytes to store the name Sam, even though VARCHAR of 10 is given. VARCHAR data type will not leave unused spaces. It releases the unused memory spaces. This demonstrates how VARCHAR efficiently uses storage by adapting to the actual characters entered, without adding unnecessary padding or wasted space. The value for VARCHAR data type has to be enclosed in single or double quotation marks. The CHAR and VARCHAR types are similar, but differ in the way they are stored and retrieved. They also differ in maximum length and in whether trailing spaces are retained. Let's see the difference between CHAR and VARCHAR date types. First point. CHAR stands for character, whereas VARCHAR stands for variable character. Second point, CHAR stores character strings of fixed length, whereas VARCHAR stores character strings of variable length. Third point. CHAR can store a maximum of 0 to 255 characters, whereas VARCHAR can store a maximum number up to 65,535. Fourth point. The CHAR data type is used when the data entries in a column are expected to be of the same size. An example would be an admission number of a school student. The admission numbers of the school are of uniform length. Another example is the PIN code column in a database of a country, where PIN codes are of uniform length. Whereas, the VARCHAR data type is used when the data entries in a column are with expected variations in data size. An example of using the VARCHAR data type is for a product description column in a database for an online store. Product descriptions can vary significantly in length, and using VARCHAR allows you to store these descriptions efficiently while accommodating the natural variation in text length without unnecessary padding. For example, if you have a CHAR of 10 column and you enter hello, which is 5 characters long, it will be stored as hello with 5 additional spaces added to make it a total of 10 characters. This fixed-length storage ensures that every value in the column occupies the same amount of storage, maintaining consistency, but it may lead to some wasted space when storing shorter values. Whereas VARCHAR of x minimizes storage usage by adapting to the actual characters entered. VARCHAR of 10 column and you enter the value hello. Hello contains 5 characters. Hello will occupy 5 bytes in storage, exactly matching the length of the text provided. This demonstrates how VARCHAR efficiently uses storage by adapting to the actual characters entered, without adding unnecessary padding or wasted space. Sixth point. CHAR of x adds blanks when a value entered is shorter than its length x. So some memory space is wasted. Whereas, in VARCHAR data type, no blanks are added if the length is shorter than the maximum length, x. No wastage of memory space. Seventh point. CHAR data type takes memory space of 1 byte per character, whereas VARCHAR takes up memory space of 1 byte per character, plus 2 bytes to hold variable length information. This makes VARCHAR more space efficient for variable length strings, compared to CHAR, which reserves a fixed amount of space per character. Eighth point. In CHAR data type, search operation is faster, as it stores fixed length of characters of a string. Whereas, in VARCHAR, search operation is slower. Ninth point. Example, name char of 10. Name equals Sam. Here, name field occupies 10 bytes, with the first 3 bytes with values and the rest with blank data. Whereas in varchar, example, name varchar, 10, name equals Sam, name field occupies only 3 plus 2 is equal to 5 bytes, the first 3 bytes for value and the other 2 bytes for variable length information. When to use char or varchar? Use char when data is of consistent, fixed length. Data length is always the same. Space efficiency is not a primary concern. Use varchar when data length varies significantly. Ideal for text data with different lengths. Offers space efficiency as it adapts storage. Common choice for variable length data. Let's discuss about the next data type, date. Date data type is used to store a date in YYYY/MM/DD or YYYY-MM-DD format. It stores year, month, and date values. YYYY represents the year, 4 digits. MM represents the month, 2 digits, 0, 1 to 12. DD represents the day, 2 digits, 0, 1 to 31. Date values can be compared with each other only. The date values to be entered are to be enclosed in single quotation marks. Example, 2023-05-16. When working with dates, you have to be sure that the format of the date you are trying to insert matches the format of the date column in the database. The date data type is commonly used for various purposes, such as tracking events, managing schedules, and recording dates of transactions or events. It is useful for storing and working with date-related information in a database, and it ensures data consistency and accuracy when dealing with date values. The next data type is time. Time data type is used to store time in HH:MM:SS format. It stores hour, minute, and second values. HH represents the hour, 00 to 23. MM represents the minutes, 00 to 59. SS represents the seconds, 00 to 59. For example, a time of a day can be taken as 10:15:30, where 10 refers to hours, 15 refers to minutes, and 30 refers to seconds. The time data type is used to store and manipulate time-related information in a database. It's useful for tasks like recording timestamps, scheduling events, and tracking the duration of events. When combined with date or date-time data types, it can represent full timestamps with both date and time components. Constraints in SQL. We will discuss about some commonly used constraints in SQL. SQL constraints are used to specify rules for the data in a table. Constraints are used to limit the type of data that can go into a table. This ensures the accuracy and reliability of the data in the table. The first constraint is the primary key constraint. The field or attribute or column which uniquely identifies each row or record in a table is the primary key. Primary key is a combination of a not null and unique. Primary keys must contain unique values and cannot contain null values. A table can have only one primary key, and in the table, this primary key can consist of single or multiple columns, fields. Suppose you have a table named employee with the following columns. Employee_ID, primary key, name, department. The employee_ID column is defined as the primary key. Each value in the employee_ID column must be unique for each employee. There cannot be two employees with the same employee_ID. The employee_ID column cannot contain null values. It must have a valid identifier for each employee. Let's see an example. SQL primary key on create table is given here. We are creating a table named employee. Here, employee_ID and name has the constraint not null. That means these fields should contain value. It should not be allowed blank. and employee_ID is the primary key of this table employee. Some commonly used constraints are not null constraint. It ensures that a column cannot have a null value. Null means missing or unknown or not applicable value. This enforces a field to always contain a value, which means that you cannot insert a new record or update a record without adding a value to this field. Sometimes an attribute or column should not be allowed blank. Let's see an example. SQL not null on create table is given here. We are creating a table named student. So here, ID and name has the constraint not null. That means these fields should contain value. It should not be allowed blank. Let's learn about the unique constraint. The unique constraint ensures that all values in a column are unique or distinct or different. Both the unique and primary key constraints provide a guarantee for uniqueness for a column or set of columns. A primary key constraint automatically has a unique constraint. However, you can have many unique constraints per table, but only one primary key constraint per table. Let's see an example. SQL unique on create table is given here. We are creating a table named student. Here the ID and name has the constraint not null. That means these fields should contain value. It should not be allowed blank. Now, you would have noticed that ID has the unique constraint also. That means all the IDs should be different or unique for all the students. No student can hold the same ID. Each student holds a unique or different IDs. The next SQL constraint is check. The check constraint is used to limit the value range that can be placed in a column. If you define a check constraint on a column, it will allow only certain values for this column. If you define a check constraint on a table, it can limit the values in certain columns based on values in other columns in the row. Let's see an example. SQL check on create table. The create table statement creates a table named student with 3 columns, ID, name, and age. The ID and name columns are required and cannot contain null values, while the age column must have values that are greater than or equal to 18, as per the check constraint. This table structure is suitable for storing information about students, including their ID, name, and age, with an age restriction applied to ensure that only adults, aged 18 and above, can be recorded in the table. The next constraint is the default constraint. The default constraint is used to set a default value for a column. The default value will be added to all new records if no other value is specified. Let's see an example. Now, look at the SQL statement. The create table statement creates a table named student with 4 columns, ID, name, age, and city. The ID and name columns are required and cannot contain null values. The age column can contain null values. The city column, if not specified during an insert operation, will default to Delhi. This table structure is suitable for storing information about students, including their ID, name, age, and city of residence. Let's learn about the foreign key. A foreign key is a field, or collection of fields, in one table, that refers to the primary key in another table. The table with the foreign key is called the child table, and the table with the primary key is called the referenced or parent table. Let's see the primary-secondary relationship. A foreign key creates a primary-secondary relationship between 2 tables. The table containing the foreign key is considered the secondary or child table, and the table to which it refers is the primary or parent table. Now, look at the tables. You have department table on the right side of the screen, which is the primary or parent table, and employee table on the left-hand side is the secondary or child table. In the department table, dsig_code is the primary key, which when related with the table employee, becomes a foreign key to it. Again, I explain. Notice that the dsig_code column in the department table on the right side of the screen points to the dsig_code column in the employee table, which is on the left side of the screen. The dsig_code column in the department table is the primary key in the department table. The dsig_code column in the employee table is a foreign key in the employee table. The foreign key constraint prevents invalid data from being inserted into the foreign key column, because it has to be one of the values contained in the parent table. Let's see an example for foreign key constraint. Assuming you have already created the parent table named department table with the dsig_code as the primary key, you can define the foreign key relationship in the employee table with the following SQL statement. Create table employee, open bracket, item_id varchar of 5, primary key, emp_name varchar of 25, dsig_code varchar of 10, foreign key, dsig_code, references department, of dsig_code, close bracket semicolon. In this SQL statement, item_id is the primary key in the employee table. emp_name is an attribute for the employee's name. dsig_code is a column in the employee table that you want to create as a foreign key. The foreign key constraint is used to specify that the dsig_code column in the employee table is a foreign key. It references the dsig_code column in the department table. This establishes a relationship where the values in the dsig_code column of the employee table must exist in the dsig_code column of the department table, which enforces referential integrity. In other words, you can't insert values in the employee table's dsig_code column that do not exist in the department table's dsig_code column. Make sure you have created the department table with the dsig_code as the primary key before running this SQL statement. Thanks for watching. Please subscribe if you are new to my Sally and Bytes YouTube channel to stay updated with engaging content and never miss out on my latest videos. If you like this video, don't forget to give this video a thumbs up. Share this video with your friends and relatives. Watch the upcoming videos, Relational Database and SQL, Part 6, How to Install MySQL on your Windows system. You can check the link in the description box given below.